listening. Yeah. So basically, we have started a series of webinar with USB Case Nest, and today's webinar is one of them. The title of today's webinar is Designing and Critical Parameters of Solar PV Systems and Components. And today's trainer is Dr. Nadia Shehzad. She is working as an associate professor and HOD at USB Case Nest. She received her PhD degree with specialization in photovoltaics from the Department of Applied Science and Technology, Italy. And she has established her expertise in PV system components, designing, sizing, and safety through different high-level workshops and training organized by PV experts from Arizona State University, USA. So I think without any ado, we should start now. So over to you, Dr. Nadia Shehzad. You can share your screen.
Thank you very much. Yes, I will just share the screen in a while. Are the slides visible?
Yes, it's visible.
Okay, thank you. Assalamu alaikum and good morning. I'm Nadia Shehzad. Today I'm going to talk about solar photovoltaic system components, with a particular focus on their designing and critical parameters. First of all, there is a question why we should discuss this technology. In my view, there are two particular reasons, or two major reasons. The first one is Sustainable Development Goals, where 7th point calls for affordable, reliable, sustainable, and modern energy for all mankind. And it is sure that access to clean energy is essential for better education, better health, and better lives. And the second important reason is its abundance. As we all know that solar energy and its capacity is renewable, and it is abundant among all other renewable as well as the finite sources. And finite sources will finally be ended, and then we must have to shift it towards renewable energy technologies. So this is the major reason to discuss this technology, I hope. And the international community is already working on this thought. You can see here at the end of 2020, the contribution of solar energy among other renewable energies was 26%, and then it has been increased to 28% by the end of 2021. And the amount has been increased from 714 gigawatt to 849 gigawatt. Similarly, if we look this capacity in Pakistan, we can see a continuous rise in installation capacity or in the cumulative installed capacity. Particularly, the given data is of grid connected systems, not the distributed ones. And there will be even more capacity if we include that part as well. And of course, we are following the renewable energy policy, which says that we have to reach 9,700 megawatts up till 2030. And I have recently seen a report by NEPRA where they have compared installed capacity and dependable capacity of different technologies, including the traditional ones. And we can see that there is a big difference in the dependable capacity and in the installed capacity. Here you can see the differences in hydel, thermal, as well as in nuclear. And these differences can be justified if we say that most of or some of these new power plants can be older, they are already aged, and sometimes we may not have sufficient fuel to run them in case of thermal and nuclear power plants. So we can justify, but we still see such kind of difference in installed and dependable capacity in case of renewable technologies, which is particularly including solar and wind. So when we talk about solar technologies, there should not be such a gap between installed and dependable capacity. But this gap can be a reason why, because the designing and installations of such systems is not up to the mark. And we must have to discuss, we must have to implement their critical criteria while designing and installing the systems. And we must discuss the environmental parameters of that site where we are going to install, because they are also critical in designing of such systems. So that's why I'm going to discuss sun and its radiations and mounting of the collectors according to the availability of these radiations. Then we will also discuss solar photovoltaic cells, modules, and arrays, their current voltage characteristics, and finally, environmental effects on the photovoltaic module output parameters. Besides photovoltaic modules, we will also discuss PV system and their respective components, and then the storage and other power electronic devices with a particular focus on critical parameters and balance of the system. Sun and its radiations. If we do not know what we are receiving from the sun and where it is maximum and in which orientation we can receive the maximum amount of photons out of the sunlight to convert them into electricity using the photovoltaic modules, then we will not be able to size the system effectively. So we must know what is sun. Sun actually is fireball, we can say. Inside it, there is thermonuclear fusion, which generates different kinds of radiations. But what we are receiving on this globe can include only some of those radiations, particularly including X-rays, ultraviolet, visible light, infrared, radio waves, and gamma ray can also be there. But we can particularly focus on visible light among these or some part of infrared, because this range is suitable for conversion into electricity. When we see the output capacity of sun around its ball, we can see that the value is quite high, 10 raised to power 26 watts, whereas our globe's total energy requirement is 18 terawatts, which can be written as 10 raised to power 13 watts only. So only a fraction of this energy can complete the whole requirement of globe. But these radiations cannot reach as it is on our globe. They reduce while they pass through the atmosphere around this world. So atmospheric effect can decrease the intensity because of absorption and scattering effects. Other local variations can also affect, such as water vapors, clouds, and pollution presence in this atmosphere. And some other parameters are latitude of the location and season of year or time of the day. These parameters can also affect the solar radiations. So we cannot assume any particular value of these radiations. We have to measure them while we are on the equator or in any other latitude location on this globe. So we need some devices. Some of these devices we also host at USP CAS in our labs. These include spiranometer. You can see here, it is a device which can measure in 180-degree semisphere So it means it can calculate all the intensity of radiations which can be available for the photovoltaic device. And another device, which is pyrheliometer. This has a small cone, a small window opening where it can receive radiations and detect them. So it is used for direct radiations only. And then another device, which is albedometer. It has two hemispheres, one on the top side and other on the bottom side. This device is meant to measure the reflected light particularly, because it can give us the difference on top side and on the bottom side. So reflectance of any surface can be measured using this device. Another is their sunshine duration sensor. It becomes active when the sunshine in the field is above 200 milliampere per centimeter square. If milliwatts per centimeter square. If the irradiance is higher than this sunshine recorder will be active and can measure whole data and log it. So we can, but it is a bit costly. Besides these devices, we can also have some gadgets, for example, reference solar cells. These are actually small area solar cells, but highly efficient. They can convert radiations into current, for example, and that current can be calibrated with the value of irradiance. So after calibration, these kind of devices can also be used for irradiance measurements. This is the simple irradiance meter. So this is very cheap solution as compared to all other radiation measuring devices. We also host a meteorological high precision station at NUST University. This can collect and log data related to wind, solar irradiance, humidity, and temperature. And the data is collected data for several years, starting from 2012, has been logged with us, and the data is also available on the web page. If someone needs this data, can ask us or can directly take from the web page of the station. Solar insolation around the map of our country, you can see it lies in the range of 5.5 or 5 or up to 6, we can say. In some regions, we also see 6 to 6.5 kilowatt hour meter square per day. So this value actually corresponds to peaks and hours. So we can simply use this data for any kind of designing. Okay, besides the intensity of radiations, we also know that sun moves its path around the day and around the seasons. When we have winter, the sun can be at lower elevation angles. When it is summer, it can have higher elevation angles. So that's why we must have to know some angles when we are going to install the photovoltaic modules or collectors. Here you can see there are 3 particular angles. The first one is solar incidence angle, which means sun should be in front of the photovoltaic module, which says that the angle between normal to this surface and the ray coming from sun should be 0 or minimum as possible. So solar incidence angle should be 0 or minimum possible. Another angle is collector azimuth angle, which says that collector should face south side always, so that it can receive maximum intensity as possible during the whole day. So the surface of collector should have angle with this line as minimum as possible, with the south line actually. So this angle, this collector azimuth angle should be 0 ideally, but as minimum as possible according to the site and availability. And then there is a third angle, which is angle between horizontal plane and the surface of the module. So this is known as collector tilt angle. How much tilted it is upward or downward, closer to the horizontal plane. So depending on these elevation angles of the sun, you see the sun will be quite high in summer. So this tilt angle should be as less as it can get 0 solar incidence angle. And similarly, when we talk about winter, so the tilt angle should be higher so that the sun should directly face the collector. So there is a thumb rule that winter performance is enhanced by tilting the collectors 15 degrees greater than latitude. And similarly, summer performance can be enhanced if the tilting of these collectors is 15 degree less than the latitude. Okay, now we have some knowledge of solar irradiance. So now we should move towards types of photovoltaic systems. There are two particular types. One is off-grid, where you can see small scale mobile systems for different displays or different applications. Similarly, we can also use modules at higher array levels to store some energy and convert it into useful electricity. And then there can also be another type of photovoltaic system which can be connected to the grid. So generically known as interactive PV system. This can also have smaller ranges or larger ranges, as in power plants, you can say. Components of such systems in case of standalone photovoltaic arrays, and then there can be some controllers to charge the battery or to run the loads. And if we have to run AC loads as well, then we can also include inverter in the system to convert DC electricity to AC currents. And on the other hand, when we talk about grid connected or interactive systems, besides photovoltaic modules, we need inverters, some particular inverters or inverters with the power conditioning systems. They can simply inject the output into our casual distribution panels that we use at home, and then we can connect it towards electric utility. So we can use this electricity to run the site loads, as well as the additional electricity can be injected to the grid. So it means the first important component of this system is the photovoltaic module or photovoltaic array. Photovoltaic module is actually made up of solar cells, and traditionally these solar cells are known as silicon-based PN junction solar cells. Any kind of cell should has capacity to convert photons coming from sun into electrons, or we can say electron and hole pairs. So the structure of this cell is made in such a way that one side we have P-type material, means high potential, and other side we can have lower potential. So because of this potential difference, the generated carrier will move. One kind of carriers will be moving one direction. So electrons are moving on the, you can say, N-type terminal, and on other side, holes are moving. So two terminals of this device will be at different potentials. You can say one is positive, the other is negative. So that's why, without changing the direction of the current. So that's why we call it direct current. This is the DC device. Okay, but the problem with a single cell is that this cell has only around 0.7, 0.6 volts. So it is not useful voltage. So we have to join different cells to make a photovoltaic module. And then that photovoltaic module can run different, you can say here, the loads like bulb or a small fan, but still it cannot be able to run the high requirements load. That's why we must have to join different modules together with each other to make the photovoltaic arrays. Before making arrays, we must know the characteristics of each photovoltaic module. So those characteristics can be known only if we can connect these modules either with, you can say, multimeter to know its short circuit, or you can say open circuit conditions. But other way is to measure its current voltage characteristics curve, which look like this. You can say when this small device is connected with the power supply and we supply power voltage starting from 0 up to a certain value, then it shows us current. When there is no voltage, we see a maximum value of current passing through the circuit. This current is known as the maximum current, or simply as there is no voltage, so short circuit current. So this short circuit current is actually the light generated current because there is no applied voltage at this stage. When we increase the applied voltage, you see there is a certain point when there is no current in the voltage, even if we have applied the voltage. If there is no current in the system, but voltage is applied. So because of applied voltage, we call it open circuit, or the value is known as open circuit voltage. So the third important parameter in this IV characteristic curve is this maximum power point. Actually, if we look at all these points, here the current is maximum, but voltage is very low. And in this side, you see the voltage is maximum, but current is very, the current will not be. So that's why we cannot get maximum power in these points, but there is only one particular point which corresponds to that maximum value of voltage and maximum value of current, which gives the maximum multiple in form of power. So this is known as maximum power point of this characteristic curve. All the devices will be following this maximum power point. We will be discussing in future. Okay, now we must know another parameter which is known as fill factor. Fill factor is actually ratio of two power points. One is maximum power that can be collected out of this device. The other is ideal power. And ideal power is actually obtained by multiplying this line and with this line. So area under this ideal rectangle. So finally, this ratio will give us the quality of the device, how best it is. So it should be just like a square or rectangle instead of a triangle. For example, if the curve is of this type, then the fill factor will be very low. So finally, now we have a maximum obtainable power out of this device, and we must know its input so that we can calculate the power conversion efficiency. What should be the input? Input is actually the irradiance, and we can multiply this irradiance with the active area of the device to convert it into power, into only watts. 1000 watt per meter square is 1 sun irradiance, the standard value. If we multiply it, active area of the photovoltaic module, we can easily get wattage. So these two powers, one is input and the other is output, can easily give us efficiency of the device. Besides efficiency, there are other parameters which are very important to be seen while purchasing a photovoltaic module. You can see here a nameplate of photovoltaic module manufactured by Jinko. We can see maximum power, power tolerance, and then maximum power voltage and maximum power current, which are also known as operating voltage and operating current, or rated voltage or rated current of the device. Besides these, we should also know the polarity of terminals. It should be clear, otherwise we will connect oppositely. Maximum overcurrent device rating should also be known. Otherwise, overcurrent device rating may not protect the photovoltaic array. Maximum permissible system voltage, that these photovoltaic modules can bear which kind of voltage of the whole array. Because when we join our photovoltaic modules to make the arrays, the voltage levels at the terminals will be very high. So the photovoltaic modules connected to the terminals may face degradation because of that voltage. So that permissible system voltage should also be written on the back side of your device when you are going to purchase it. Okay, efficiencies and different types of photovoltaic modules. There are monocrystalline and there are polycrystalline photovoltaic modules, which are very common in this field or in commercial market of this field. You can see there in mono appears in black, very homogeneous color, and they can have cut corners, not much, but they can usually have cut corners. They have record-breaking efficiencies of up to 23% in module levels. On the other hand, polycrystalline can be bluish color. They can have sharp corners, and they can be shaded in different shades, light and dark blue shades. But they can give 18% of efficiency. On the other hand, they have lower cost, surely. Besides mono and polycrystalline silicon, we have other technologies generically known as thin films, cadmium telluride, amorphous silicon thin film technologies, copper indium selenide, or you can say copper indium gallium selenide. So these all technologies are also commercial and available, but their efficiencies are not that high as the monocrystalline or even the poly. You can say the commercially available modules usually show the efficiencies in these ranges, which are surely lower than the record-breaking efficiencies. But what we are receiving from particularly China, those modules usually show efficiencies in this range. But of course, they have lower cost. The area required per technology also varied depending on the efficiency. You can see the lowest area is required for monocrystalline, and similarly, the highest will be required for amorphous silicon. But on the same side, you can say the cost is also highest for monocrystalline and lowest for amorphous silicon. So this is a trade-off between area and cost. Another factor is very important to know is the annual degradation rate. It is higher in thin film technologies, and the most degrading module is amorphous silicon. But at the same time, we know that its cost is also low. So we have to trade off. Besides these traditional technologies, there are some new technologies as well. For example, half-cut cell and bifacial photovoltaic modules. You can see they can have different structure as compared to the traditional photovoltaic module. It has different multiple strings on both sides connected in parallel with each other. That's why this half-cut cell technology without bifacial, and these three are without bifacial, and this is half-cut cell technology along with the bifacial. So if we talk about only half-cut cell, they can have less power losses as the cell area has been reduced, and they are more tolerant for shadowing losses as there are multiple strings connected in parallel. So if one is shaded, the other will be working. Bifacial can also give us enhanced performance as we can receive irradiance from both sides. From the top side, direct irradiance or global, and from the back side, the diffused ones. Okay, besides the technologies, we should also design the photovoltaic arrays depending on single photovoltaic module characteristics. If we know its all characteristics, particularly voltage and power ratings, then we can join different modules in series to enhance its voltage. And then if we joined these strings of different cells together with each other, then at that stage, we will be enhancing the power. Then voltage will remain same. So different arrays can be made. And these arrays can have different output voltage levels. For example, if we have connected some number of modules in, for example, parallel, then you can see that voltage will remain same and current will be added up. If we have connected some modules in series, then of course the voltage will be enhanced and the power rating or the current rating will be same. Finally, we have to calculate the area required for photovoltaic array installation. This area will depend directly on the single photovoltaic module's power rating. But besides this, this will also depend on some other parameters like environmental parameters, situations, wind flow. If we first calculate the area required for the total capacity of the array, for example, if it is 4 kilowatt, then we need 23 meters squares to install 350 watt photovoltaic modules. Besides this, we will also consider different environmental factors and other situations to maximize the performance and safety of the array. Temperature range. If the temperature range is wide for summer and for winter, then we should also consider it among all the calculations of voltage. For example, if the temperature is higher in summer, the voltage will be reduced. Similarly, if the temperature is lower in winter, the voltage of the photovoltaic array will be increased. So this wide range should be calculated at the time of design of PV array. And then we must also consider the irradiance levels. Irradiance level, with the decreasing irradiance levels, photovoltaic module performance will be decreasing. And then we must also consider maximum wind speeds, fire safety codes, and accessibility. Considering these all factors, we have to decide the size of arrays and separation between different arrays. And we should also consider seismic or heavy snowfall regions, because this will define the strength of the structure on which we are going to mount the photovoltaic modules. Just to show the temperature effects, you can see the voltage for this curve where the temperature is 0 degrees is best. But for the blue line, you see where the temperature is around room temperature, it is lesser than 0 degrees. And then for higher temperatures, you can see further decrease in voltage. So this must be noticed while designing. Here you see the irradiance, a uniform change in irradiance, which can be because of clouds or environmental factors, other environmental factors. Then we can consider this in designing. Shading can also be non-uniform. As you can see here, different shades because of trees or leaves, or these shades can be because of soiling or bird droppings. So all these environmental factors should be considered in designing, and we should avoid the locations where these shade can maximally affect the power loss. You can see a partial power loss can affect partial shading can affect some power loss, but a substantial power loss can be seen if this kind of shading is covering whole of the bottom side of this module. In this case, all the strings are actually being inactive or will be affected, will have lower power output or degraded performance. As you can see, such kind of shading can be seen if the row spacing is not considered while designing. For example, if we have sun at higher elevations in summer, then we see this height of photovoltaic module will be less as the tilt angle is lower. But if sun goes down in winter, we must have to raise the tilt angle by 15 degrees as we discussed earlier. So this height will be higher and the shadowing effect will be more on, and it may cover the other row as well. So we must design these row spacings considering the, you can say, lower sun levels or higher tilt angles. In that case, there will be no shadowing in the rest of the seasons. Another good way to avoid shadowing is to use half-cut cell technology, because half-cut cell technology has different strings connected in parallel to each other, if there is shadowing on one part, only that particular part will be affected, but the rest of the module and the rest of the strings will be working well. Okay, after photovoltaic modules, we must also know about batteries, which are storage systems, and the charge controllers, which are going to store in batteries at safe voltage levels and voltage and power levels, you can say. Another device which should be known is the inverter, which can run the AC loads. So starting from batteries, we know there are primary batteries which cannot be recharged, and there are secondary batteries which can be charged. So secondary batteries can be used for solar photovoltaic system applications. But again, you can see there can be starting, lighting, ignition batteries. There can be standby or stationary, which are not recommended for photovoltaic system. But motive power or traction batteries can be used. Among these batteries, we see lead acid, sealed or flooded, both are recommended. Lithium ion can be used, nickel cadmium can be used, sodium ion can be used for this application. And there are some critical parameters which must be considered. For example, electrical properties, which include voltage levels, capacity of the battery, and then charge and discharge rates. Performance is depending on cycle life, depth of discharge of the battery, which is claimed by the, you can say, manufacturer, and then system autonomy, means for how many days you are going to design this battery storage, even if the sun is not available. Other parameters include size and weight, maintenance requirements, installation related to location, structural requirements, environmental conditions, and then safety, auxiliary systems. And finally, of course, warranty and availability of type of batteries is also imported along with the cost. Battery state of charge and depth of discharge. When a battery is fully charged, the state of charge will be 100%. And then we will start discharging the battery, and then the depth of discharge will be increasing. You can say up to 70%, we can consider the allowable depth of discharge up to around 70%. But better is to go down to 60%. This is usually recommended by the manufacturers as well. And then the capacities and other important factor to know about. Capacity of battery is also linked with voltage. You can say the voltage capacity curves are here. This is the nominal voltage. When we charge the module and the battery, then we will get the nominal value of the voltage. But when we start discharging it, the voltage will also be decreasing, and we will reach, after a certain discharging level, you can say up to DOT, there will be cut off voltage. So we must cut here all the, you can say, disconnect here all the loads from the battery. So DOT corresponds to the cutoff voltage, and this is the value where we have to disconnect the system. Battery capacity relation, here is a simple relation. If we know the electric requirements of the load, and we know the days of autonomy, or if we do not need days of autonomy, we can use only one here. We know DOD, we can know the DC voltage of the battery, and then finally the limiting factor. The limiting factor depends on type of the controllers and their efficiencies. So we can finally calculate the battery capacity if we know the load and other requirements. If we know the battery capacity, required battery capacity, to reach that required battery capacity and voltage, we have to join different batteries. For example, if we have 12-volt batteries, then we can join them together with each other to increase the voltage levels in series. But if we join them in parallel, then we will not increase the voltage levels, but we will be increasing the ampere hours of the battery, which is actually capacity of that battery. Okay, so after designing, we have to charge, and the charging should be controlled. It usually has 4 stages to charge, where first one is bulk stage, where current remains constant. At maximum possible current, we will charge the battery, and the voltage will be, of course, increasing while we go on charging. Around 80% charging should be done in this stage. Then for the rest of 20%, we go for absorption stage, where the voltage is kept constant, so the current will be reducing. And finally, we reach in float stage, where both the parameters will remain constant. So now if we leave the battery after float stage, connected to the photovoltaic modules, the battery may go on, you can say, heated up, because the temperature of the electrolyte, particularly in case of lead acid batteries, will be rising, and we may see some evaporation or loss of electrolyte. And so both of these, temperature rise or loss of electrolyte, will be degrading battery's life. So overcharging is not allowed, is not recommended, and at the same time, if we do not charge the battery completely and keep it undercharged within the bulk stage, and the chemistry of that battery will disturb. So undercharging can even be more detrimental. To make the chemistry reversible, we must completely charge the battery. You can see here, we should discourage frequent undercharging. Why? Because the overcharging is detrimental. Again, the severe overcharge can further decrease the cycles of the battery life, but undercharging is really severe or damaging to the battery life particularly. Okay, who will control this charging process? The charge controller. The charge controller should avoid the overcharging, and as soon as it test or check that the battery is nearly filled, or the charge has been stored and the voltage or nominal voltage has been achieved, it should disconnect or modulate the power coming from photovoltaic modules. And then if we have been achieved the lowest or low state of the battery, you can say close to DOD, then the charge controller should disconnect the loads to protect the battery from over discharge as well. So battery should not be overcharged or should not be over discharged. To control these parameters, we have 4 set points for controller. For example, you can see here voltage regulation, at which we will disconnect the photovoltaic array from the battery, and then array will be reconnected again at this array reconnect voltage. Then there are other 2 voltages which are important for the depth of discharge or for discharging process. You can see low voltage disconnection, where we will disconnect the load, and then again load will be reconnected at this LVR value. These parameters can be seen within a battery schematically. Here you can see nearly above top 10% is connected to the high voltage disconnect and reconnect, whereas when we talk about load, 10% above, you can say the DOD value is linked to the lower voltage levels for LVR and LVD. So finally, we can protect the battery from overcharging and over discharging using the controller. But when we select the controllers, we should also consider the following. For example, types of the batteries. If we are using flooded batteries or maintenance-free deep cycle batteries, these values can be different. So if we know the battery type, then we can finally select the good or suitable controller for that battery charging. Again, we should also consider temperature compensation. Similar to photovoltaic modules, there is effect of temperature on the cells of battery, you can say. Battery's temperature is increasing then its regulation voltage will surely be lower, which means that nominal voltage will be sure, cutoff voltage will also be different. So we should control these parameters, and to control these parameters, we must also know the temperature compensation coefficient. For example, for lead acid batteries, the value is -5 millivolt per degree centigrade. And there can be another important parameter, equalizing charge, for particularly for the flooded batteries. Equalizing charge is just a deliberate overcharge which we can give to the batteries after some recommended time using the charge controller. And this overcharge can finally refresh the electrolyte, and particularly you can say the electrode of that battery. But it is only recommended for flooded batteries, not for, you can say, sealed or other batteries, solid state batteries. Charge controller sizing should be done as per the following criteria. For example, when we know the maximum output current of the photovoltaic module, then the controller should be sized for at least 125% of that value, because controller, not only controller, but overcurrent protection devices and control other, you can say, equipment, for example, wires, should also be sized for this value. You can say 25% can be added for controllers, or 25% can also be added for wires and other, you can say, values, because there can be some certain kind of losses in this system. Here is an example. For example, if 16 amperes should be required, then we should size the controller for 20 amperes, 25% of 60 amperes. And then for other conductors, we should also consider another 25% rise. So 25 amperes should be considered for designing. And this charge controller can be connected with the battery. You can see should be placed very close to the battery as well. And here you can see the connections for the load, connections for the piece of it. It's very simple to connect. But there is a complication if we have to place battery far away from the controller. In that case, while transferring amount from battery towards the controller, the voltage will be dropped, and the controller will not be able to judge the actual voltage levels of the battery. In that case, we can use the batteries with 4 connections, the controllers with 4 connections, and 4 connections will be connected on the 2 terminals of the batteries. Here 2 cables will be working as power transfer, but the other 2 will be working as voltage sensing cable. The voltage sensing cable is actually carrying very low amount of current, so there will be no voltage drop. And the, you can say, controller will be actually judging the battery voltage. If we have to run the AC loads, we can further connect the inverter in the same system, which will also be controlled by the controller and will get voltage from the battery for the standalone system. Anyway, inverters can be 95% efficient, and you can see as homage is the very good quality here we get in Pakistan. It usually based on pure sine wave recommended for the photovoltaic modules or arrays, but not square or others for particularly for Pakistan. So these inverters can simply convert the DC or direct current into alternating current with efficiency of 95%. Further, we should also distinguish these inverters based on the type of the power system. For example, for standalone, we must always remember that its input will be coming from batteries. So it should be sized as per demand, or the battery should be sized as per demand of the standalone inverter. On other hand, when we talk about interactive inverter, there is no battery or there is no storage between So interactive inverters are actually difficult to size because their input is coming from photovoltaic arrays, and photovoltaic arrays are not providing the constant output parameters. So that's why we must consider the temperature and irradiance variations in sizing the inverter. Inverter's output will surely be according to the utility grid. So for standalone, we can size the battery according to the power requirements of inverter. You can see here simple relation that gives the battery capacity depending on power requirement, time for which we need the supply, and the DC voltage of the battery, you can say. So finally, or the input, DC input of the inverter, you can say. So if we have the battery capacity, you can finally choose the inverter ranges. But when we talk about interactive inverter, as the output of photovoltaic modules will be varying, so the DC input voltage will also be varying. That's why the inverters should have wide DC input range, and or it should accept this range. Usually we use MPPT inverters for this application, and as you can see, such kind of inverters have two ranges. One is operating range and the other is maximum power point range. So if we want to get maximum output from this inverter, the input parameters should be aligned with this MPPT range. But for critical seasons or times of the day, the wider range of this inverter is operating range. Below this inverter range, if the voltage, input voltage is lower, then this will not work. But if it goes beyond this upper limit, then the inverter may be damaged. So we must consider these two extremes of the, you can say, photovoltaic array parameters, particularly the voltage. Okay, so summarizing, photovoltaic module arrays, and then and then the inverter required. You see the power, DC power output of the DC power output of photovoltaic array should be sized according to the AC output requirements of the inverter, and this value should be at least 110% of the AC output power rating. Why? Because there are losses in the inverter, and there is another severe condition of, the temperature, as the DC input will be varying widely. So we must, power will also be varying. So we should avoid the losses, and that's why we must size the inverter more than 110% or up to, you can say, 130%. Hence, finally, we can say that voltage must be above the minimum inverter operating value and MPPT voltage during hottest operating conditions. On other hand, we can also say that voltage must not exceed 600 volt DC if we are designing it for residential, and if we are designing it for, you can say, commercial levels, then this value should not exceed 1000, because these two upper caps have been applied for safety concerns. Or the maximum input, you can also say that the array voltage should also not exceed the maximum inverter operating voltage during the coldest operating conditions. So finally, we know the all critical parameters. To design the system, we can start from photovoltaic modules in case of an inverter, interactive inverter. So the photovoltaic array can have some particular device rating. So starting from that nameplate, we know 0.9% will be degraded. Okay, so just considering the nameplate rating. And then besides this, we should also consider some other derating factors. For example, inverter or transformer module mismatch losses, DC wiring or AC wiring losses, Soiling losses can also be because when we install photovoltaic modules in environment, the soiling can also be more on some particular regions. So we should consider that factor, that derating factor, according to the environment. Similarly, if there is shading, we should also consider that factor. Sun tracking, if there is, or aging, we can also consider its factor provided by the manufacturer of photovoltaic modules. Finally, when we have all the factors, derating factors, then we can multiply them together to get a combined derating factor. So designing should also consider these derating factors. For photovoltaic modules, we can also consider them for all other parameters, all other, you can say, devices or components. Okay, besides this, you can say temperature effects have also been considered, and then the irradiance, whatever it is available. For example, here 6.6 has been considered for a particular site. Then solar radiation received per day will be this, and finally the output will be calculated depending on the availability of sun. So this is all about sizing and designing of the system. We usually organize workshops by 2 times in a year, or sometimes you can say 3 times in a year, for different levels, for beginners and for advanced levels as well. We have some different other devices which helps us in hands-on trainings during the workshops. For example, solar kit. As you can see it here, it includes different components which the participants can join with their hands after designing. They can also measure all different levels of irradiance from different surfaces and different positions. And besides this, we also have 3 kilowatt and you can say 10 kilowatt small systems installed at GSPCAS, and also a larger scale 250 kilowatt system up to 500 in 2 different locations. So we can offer you such kind of workshops, the listeners. So must join us. See you somewhere around. Thank you. Any questions?
Thank you. We have a question in a chat box. It's a question from...
Okay. I'm just going to open it. What is the recommended tilt angle for maximum production? Yes, the recommended tilt angle is, you can say, is depending on the location, latitude angle. In winter, it is less, you can say the tilt angle should be higher, around 15 degrees higher than the latitude. So you can say it should be around 40 in most of the locations. Or for summer, it should be lesser. For example, it can be around 20, 24, 23. Depends on for which location you are asking. And another question is about ITL angle of solar panels. I think this is the answer already provided. Yes, any other question?
There's a question that what is the appropriate rows spacing between solar arrays?
Yes, it actually varies for the, of course, height or length of the photovoltaic modules. It should be, you see, less, it should be more than the shadow. It should be more than the shadow, whatever it is, depending on, of course, the tilt angle of the photovoltaic module, and you can say the elevation of sun. So if consider we are talking about winter, because in winter the tilt angle is more, so the shadow is more, and sun is at lower tilt angles. Sun is at lower altitude angles. So that's why we can measure the shadow length, and then that can be considered as the minimum distance between the two rows. So we can do it on site, wherever we are going to install.
Yes,
Yes,
we have which one solar panel is better, monofacial or bifacial? This question is from Imran.
Yes, when we talk about mono and bifacial, then there are several ideas. You can say in case of bifacial, we must also consider where we are going to install. For example, if we have to install it on a in front of concrete wall or concrete ground, or we are going to install it on grass. If we are going to install it in front of something where there can be more reflected light, then of course the bifacial will be giving us more power performance. But if we are going to install any place where there is less diffused light, any darker place, or less diffused light is available, then may not be that high performance. So, but of course, bifacial gives us better performance depending on the installation condition. Most critical factor while calculating the performance ratio of solar plant. Most critical factor, one most critical factor? No, there are several most critical factors depending on every, you can say, component. The first one must be the irradiance and direction or location of sun. And then the second should be, you can say, balance of the system. Photovoltaic modules, their output, and then other components, for example, controller should be according to the batteries, inverter parameters should be according to the photovoltaic modules if it is interactive. Otherwise, it should be according to battery if it is the standalone. So there cannot be not single parameter which is the most important. So these few parameters which are critical. Typical efficiency range of solar cells is actually, you can see it here. Typical range is from 10 to around 20. But even 8 to 20, you can say 8% in amorphous silicon, and then 15 to 20% in others. Okay, another question, what times are considered for calculations of inter-row spacing? As we have already discussed that we should calculate this value for winter when there is lowest elevation angle of sun and highest tilt angle for the photovoltaic module. Back surface is not good reflecting. It means we lost the rear side power. Yes, of course, this is true. If the back surface where we are going to install the photovoltaic module is not good, then bifacial will not be good, will not be providing better performance. But even then we will have rise, we must have rise, but of course at higher cost if we are not achieving the maximum, then this will not be beneficial. We must make changes. We can put some white paints, some reflecting paints on the back surfaces of photovoltaic modules, not back side of photovoltaic modules, on the surfaces which are beneath photovoltaic modules. Yes, number of photovoltaic modules in series can be dependent on voltage requirements and then number of photovoltaic modules in parallel, or you can say strings in parallel, will be decided based on the power requirements. When we put in series, the voltage will be increasing, and when we put in parallel, the power or current will be increasing. Any other question below? Yes, the presentation, I hope, will be shared.
Yes, the question that we have got most from the participants, that the presentation will be available on the official website of energydesk within 2 to 3 working days, and the recording of this webinar will also be available on the official YouTube channel of SMIDA. Yeah. So if you
Okay.
have any question, then you can ask, and we will wait for a few minutes, and then we will find out.
Okay.
Yeah, so we have a 2 questions from Kashif Shabir and Hisham Mohiddin in the chat box.
Yes, typical efficiency range of solar panels is this one.
It's a C30 watt solar panel can give how much
Okay.
power? Yeah.
How much power in a day? So we just have to multiply it with the, you can say, peaks and hours. For example, if we have 5 hours of peak sun during a day, then we will multiply it with this wattage or rated wattage of the photovoltaic modules to get that value. So it depends on the peaks and hours in a defined space, in any location. Now in Pakistan, we can usually consider it 5 to 6, but still there are differences in different locations. Bifacial module, the heat is absorbed more as compared to monofacial. True, the temperature is actually encapsulated within the 2 glasses, top and bottom glass. As compared to glass backside, glass on the backside, we can use some plastic sheets which must be transparent but may not be that friction free. They may, if we use those sheets on top side, they may show abrasion with time. So there is a solution in form of replacement of lower glass with a sheet which can give out some temperature. So you can say which can transfer temperature from interior part of the module towards the back surfaces, towards the environment. Any other session and problem faced by yes, I have already told that we are available at USP. So we can organize different level of workshops frequently. So installer or designers or industrialists can connect with us for such kind of solutions or discussions or knowledge, whatever you want. You can also visit us. What will be the criteria to use the solar panel installation, taking Pakistan as current scenario? Question is very wide. Criteria include different parameters, of course. So first of all, we will consider the temperature range, and then we will consider the peaks and hours for each day. And then we will design the arrays and calculate their output parameters. And after array designing according to this environment, we can then go for other components. The question actually covers the whole presentation.
So I think we don't have any more questions right now.
Okay.
Okay, so ma'am, I would like to again thank you very much for this presentation. It was really a wonderful session, and I hope everyone get a very useful knowledge. So it's all from our side. Thank you so much.
Okay, most welcome, and thank you for inviting me for this useful time together. So I hope we will have further opportunities to discuss further.
Sure. Okay.
Thank you.
Allah.
Goodbye.
Thank you.
Allah Hafiz.